Stop. Okay, there. Right. Concurrent programming on the Raspberry Pi 2.
Hello, so my name is James Hobro. I work just over the road at CamJam10 Gould Research, and I do high performance computing and physics and stuff like that. But I also play with the Raspberry Pi in my spare time. So, and given that we've now just gone through this transition from the Raspberry Pi B Plus to the Raspberry Pi 2, the hardware has changed fundamentally because now we have a multi-core system. So the two devices look very similar, disarmingly similar if you just look at PCBs, but the key difference is in the system on chip, which has gone up a number in Broadcom numbering, and that means that we have an increase in clock speed. We have a support for slightly more sophisticated instruction set with the ARM-v7. We have a bit more main memory, but most dramatically we now have 4 cores in the system. So what I'm going to be talking about today is how to, some ideas about how to get the most from those 4 cores, starting with a few simple ideas and then going on to the stuff that you might need to think about for writing Sirius code that uses all 4 cores. I'll start with some definitions then. So what I mean by sequential programming is programs that look like this, the sort that we've been writing since we started programming computers, and where you have a sequence of commands that might involve loops, decisions, and function calls, and all sorts of things like that, but at any one time, the system is reading and executing a single command. So it's a processor that's one processor that's working on one part of the code. And when you enter a function call, then of course the processor is working inside the function call, and nothing happens until you come out of it. The program doesn't continue until you come out of that function call. What I mean by concurrent programming is something that looks like this. We have a baseline, which is a sequential program, but at some point we execute a function and say, well, actually, I'd like to run that task function, whatever, in the background. And the main program continues, and the background program runs potentially at the same time, and then at some point there's some joining up. So concurrent programming is all about remaining responsive, so applications that need to be able to respond to user interaction and do stuff in the background. It's also all about non-deterministic ordering, so as soon as you start writing code like this, you have to deal with the fact that you're never sure in which order things are going to happen, which makes it much harder. The execution could be simultaneous, but it doesn't have to be. And that's where the difference is. We get the difference between concurrent programming and parallel programming, which is all about simultaneous execution, where we want to run something, we actually want to distribute it across a number of different cores. So parallel programming is about dividing up work, about actual simultaneous execution, about getting high performance out of what you've got, and about scaling, so that when you throw 2 cores at a problem, you want to try and get it to do twice as much work as if you threw 1 core at it. So I'm going to cover 3 options here. I tried to start off with something that everyone could do, and then move on to more interesting things later on. Option 0 is not to do anything, which is the easiest one, of course. Option 1 is to use the concurrency that's built into Unix and built into the entire system, and use it in nice, simple ways that Unix provides. And option 2 is to start, if you're writing a Sirius program that really wants to make use of 4 cores and their full potential, then there are various programming techniques that we need to explore to do that. So if we do nothing on the Raspberry Pi 2 compared with the Raspberry Pi 1, we get quite a significant uplift, because if you run a single sequential process on the Raspberry Pi 2, you get the entire core to yourself. And so this top core in the diagram is your process, and you get 100% of the potential of that core. And then the other 3 cores do stuff in the background for the operating system. And so that gives us some concurrency, but there's a long way to go. And actually, we had this in 1984. I don't know if anyone remembers this system. I got to play one of those when I was 12 years old, and it was an amazing thing to play with. But it was a multiprocessor home computer in 1984, and it works exactly like this. You run your program, you run a sequential program on one processor, and the other processor just did all the stuff in the background that needs to be done. Okay, that's the baseline. That's what you have without doing anything. So then there's the stuff that you can do within Unix. So, of course, most Raspberry Pis are running Raspbian. Raspbian is Debian Linux, really. Debian Linux is based on Unix. The whole of the system is a Unix infrastructure. And so when I say Unix, I'm really talking about Debian Linux and its inheritance from Unix. But that system is designed for concurrency and was from the beginning. So if you just fire up a normal Raspberry Pi, you get about 100 processors running in the background, unless you're doing a lot of extra stuff. And they will be distributed over those 4 cores quite nicely. And any sets of processors that you start will then automatically be distributed over those 4 cores. And when processors communicate using pipes and message queues, which is the Unix way of communicating, then the system will just do the work for you, and the kernel will work out where to put the processes in order to balance things. So the simplest way to do this is to, if you've got some work to do, then form it as a pipe in Unix. So the Unix pipe is entirely sequential in terms of the diagram. You read some data, you do one bit of processing on it, you pass it to the next bit of processing. But all this, Unix does this really well concurrently. On the command line it looks like this. You just use the Chevron operators to direct stuff into processors. You use the pipe operator to pipe things from one process to another. And so I came up with a really trivial example of the Unix pipe here. We've got the text of Hamlet, and we want to make some changes to names. And it's going to unzip the text. It's going to do a whole load of changes using sed. And so it's running 6 change processors, and it's running a zip and an unzip. And I thought I'd just show that running on. So here, this is the Raspberry Pi that's on this little robot here. On the right, you can see Conky, which shows us which cores are doing what. So here we've got our 4 cores, and you can see what they're all doing. And I'm just going to run that command. And it actually is processing 100 copies of the text of Hamlet, because Hamlet's so short. It's only 4 hours. It's so short that it can be processed in a matter of a fraction of a second by the Raspberry Pi. But we've got all 4 cores going at 100% here. And what's happened is that although these sed commands and gunzip commands, they need different amounts of processing, then it balances it all nicely on the system. So the easiest way to use all those 4 cores is to make your processor small and chain them together, and the pipe is the simplest way to do that. But not everything is as simple as a pipe. The other thing that's really simple in Unix that will allow you to run things concurrently is the background processes. So in the shell, you can just start something in the background. You can start as many things in the background as you like. And when you do that, this is a trivial thing that just occupies a core. Yet the S command will pump out data, and you'll be pumping it into nothing. So it gives the core something to do, and you can see it doing it without it actually having to do anything useful. And then you can see the jobs running in the background. So while you're on your Raspberry Pi here, so I've just fired up one of these background processors that doesn't do much, but you can see we've lit up a core there. If I fire up another one, it'll light up another core. These could, of course, be useful processors that are doing what you want them to do. And then you can manage these jobs just by typing jobs. And one of the jobs is Conky, which is telling us what's going on here. But I'm just going to kill them now. So I kill number 2. Kill number 3. And you should see them disappear. So what you should be looking at most of the time when I'm showing you this is these bars, these CPU bars on the right. You can see there's one of them that's still lit up, and I'm about to kill it off. So Unix has the tools for us to do this concurrent processing. The pipe and background process is the simplest of those tools. So you might think, well, let's say I've got some work I want to do. So the next example I'm going to show you is a montage example. So I've got a load of photographs. I want to do a montage. I want to rescale the photos, put them together in a montage. So that's something that's embarrassingly parallel, right? We've got how many photos? 100 photos or something. It ought to be embarrassingly parallel. So how do you write a script to do something like that? Well, that sort of job is a fairly typical job that we might want to tackle. And you can write a script which will define some jobs and launch them in the background in exactly the way I've just shown you. And then in your script there's this, so the Unix shell has this nice wait command. And so that will launch 4 jobs. They'll run on your 4 cores. Then when they've all finished, then the program continues. So this is a nice, neat way in the shell of doing stuff in parallel. That's fine as long as you're restricted to you know exactly how many jobs you want to execute. But let's say that, so here's an example of the montage that I just mentioned. So we've got some big photographs in a directory here called full size. So, and we want to scale them all down to equivalents in another directory called thumbnails. And we're going to use convert, which is from ImageMagick. It will just scale images. And we want to run this. We want to be able to run 4 of these at a time, right? So the obvious thing to do, well, you know, I'll just start them all up. I'll put my ampersand at the end of the command here. It'll run them all in the background, and then once they're all finished, I wait for them to finish. This shell script will actually crash the Raspberry Pi, and the reason for that is that there could be 100 of these photos, and so it'll be trying to start up 100 of these convert processes, and they'll all be using a certain amount of memory, and before you know it, you try to allocate processes that fill up the memory on the Pi, and the real limitation for processing on the Pi is always going to be the memory. And so this would work on a PC with 8 cores or something like that, but it won't work on the Raspberry Pi. It just doesn't have enough memory for you to be able to fire up large numbers of processes all at once. So how would you tackle a problem like this? Well, there's a very simple way, and the tool Make in Unix gives us a way to deal with these problems. And Make is fantastic. It's not just for building code. It's normally used for building code. So what Make is designed to do is to take source code, so you have your C source file, and it will build an object file from it. And of course, it can do lots of these, and this is a parallel type of operation. Normally, if you're building some code, you've got lots of source files. You want to build them into lots of object files. Then so those source files might be generated by something. They might be generated by scripts, some of them. And then you normally want to take the object files, put them together in a library, and then you want to build something that uses that library. So you've got more code. You're building another object file. You're producing an executable which takes this bit of code and it links to the library. So that's the typical use case for Make. So our problem here looks very similar to that. We've got some pictures here. We want to reduce them to thumbnails. They all work in parallel, and then we produce our montage at the end once we've got all the thumbnails. So how can you do that in Make? Well, it turns out that the Make code to do that is really trivially simple. The main part of the code, really, so what we're doing here is we're giving Make patterns. So we're telling Make that if I want to generate a thumbnail from a full-size image, then this is how I do it. I use convert. I take the full-sized image, and then I convert it and I write it out as a thumbnail. So that one line of code tells Make how to generate each thumbnail from each full-size picture. And then at the end, we want to make our montage, and there's the 2 lines of code which tell it how to make the montage from all the thumbnails once it's got them. This stuff at the top is just the Make syntax, which will give us our list of originals in the full-size directory. It gives it a list of the files, and the thumbs, it gives it a list of the thumbnails files, which are needed by the stuff underneath. Now this is high-level programming because we're no longer writing in sequence here. We're telling Make, well actually you've got these relationships, and Make can now decide how many processes to fire up and when to fire them up, and Make can make the decisions about resources for us. So this is a much higher level of programming the problem, and it's no longer sequential. So I'm going to just show you that in operation. Okay, so I'm going to do the sequence first. So if I just type Make, then it starts running these convert commands. So you can see a whole load of convert commands coming at one at a time, and each one takes a few seconds. And we've lit up one of our CPUs here, and actually every time it runs a convert command, it potentially moves from one CPU to the next. So it's not always the same one that's lit up. And so you might see the transition there looking like it's actually working in parallel, but it's not. It's using one core at a time. But Make has this fabulous option. If I run that to completion, it'll take about 40 seconds to do the whole of this job, which is 16 photos down to thumbnails into a montage. I'm just going to do Make clean, and now we'll run it with this argument minus J4, which tells it to run 4 jobs at a time. So now it's immediately started 4 of these convert jobs. We're lighting up all our 4 CPUs, and it runs approximately 4 times faster. So just by writing those few lines of code, by telling Make what it can do, then Make has made all the decisions for us, and we haven't run out of memory. We're using, okay, here's the montage. This is these 2 children and my wife here are all on these pictures somewhere, and it's from the Tour de France. But it's only 12 seconds, which is almost 4 times the speed of the sequential version. So I looked at this problem in terms of the scaling and how well it scales, and these are the times that I measured on. So the number of parallel jobs that you execute, it doesn't have to be just 4, because we've got 4 cores to work with, but you can run more than 4 jobs. And sometimes you get the benefit from running more jobs than there are cores on the system, because each one of those jobs might not necessarily be working at its CPU all the time. There might be points where each of those jobs is waiting for something from I/O or something else. And so if you run 8 jobs perhaps on the 4 cores, you might actually get better throughput than just running 4. In this case, then I didn't find that. The time is improved down to 4 jobs, and then it's basically flat. And this is what the scalability looks like. So this plot shows you how well it scales, and you'll see lots of plots with high performance computing and scaling. You see lots of plots that look like this. So we have the number of cores along the bottom, we have the speed up along the top, and we start with 1 and 1. And what we really want to achieve is this linear scaling. If we throw 4 cores at the problem, we want it to do it in a quarter of the time, ideally. In a magical world, we want it to do it in even faster than 4 times the speed. That's pretty rare. And most people are very happy if they get anything close to linear scaling. And this problem is not far off giving us linear scaling. It's a good problem to throw this to. The reason why this doesn't go right up to that line is that there's some contention in the system. So we've got our 4 processes all running together. And contention is when they're all arguing over something. And that can happen at lots of levels. It can happen at the level of accessing main memory. It can happen at the level of accessing level 2 cache for this architecture. It can happen at the level of accessing the SD card to get stuff off it. So at some stage, they can't all work at full capacity. They end up waiting for each other. But it's not bad. This is a pretty good scaling result. Okay, Makefile is straightforward. So this is the main bit of magic that I wanted to show you, the simple part of this talk. I think this is a great way to get good scalability out of the Raspberry Pi 2. Okay, I'm going to mention 2 other systems that are used for concurrent and parallel programming, but I'll just touch on them briefly because they exist and you might want to deal with them, but they're not what I want to focus on in the second part of the talk. So the first is the message passing interface, and this is a really venerable way of running parallel computing. It's been around for quite a few years now, and it's used a lot on high-performance computers. So the way that it works is that it will start n processes, which might not necessarily be on the same device. They could be on multiple devices across the network. They could be on blades in a cluster. And each one of those, each one of the programs running on those separate cores is sequential. But every now and then, they're allowed to communicate. And so they can exchange in pairs, or one of those programs can send out information to all the others, for example. Or you can be a kind of a collect process where the information from all the other nodes get collected by one node. This is a very common system for high-performance computing. It can be used on the Raspberry Pi, so it's normally used for this sort of thing, simulations, where you've got a big simulation, you want to split it up. So here I've split it up into 16 domains, and you would run 1 domain's worth of work on each of your 16 cores. You might have 4 Raspberry Pis connected across the Ethernet, for example. And you could use MPI to solve a problem like this very, very readily in that kind of system. It's mainly useful for highly symmetric systems, so where you're doing the same thing in all the cores. And so if it's completely symmetric, MPI is very good. There's also OpenMP, which has also been around for quite a while, which takes a completely different approach, where you write a sequential piece of code, and then every now and then you've got something that you want to run in parallel. And this is done with compiler directives. And so most of the code is sequential, but if you have a big loop, then you can put some directives in which will say, well, actually, I'd like to run the instances of this loop. I'm looping over a large number of items. It'll distribute them out through a little thread pool of however many threads you configure it to. And the nice thing about OpenMP is that it's built into quite a lot of packages. So I'm going to show you an example in a minute of it being built into OpenCV, which is a computer vision package, which is quite handy if you're making robots that can see. And so often you can take an existing package, you can recompile it to fire up the OpenMP version, and then you can just use it, and you've instantly got parallel capabilities. So I actually looked at the scalability of this with the Viola-Jones algorithm, which is the most common facial recognition algorithm in OpenCV. And I was rather disappointed with the scalability that it gave me. I'm still using it in the demo that you'll see in a moment, but the scaling curve is nowhere near that linear scaling line that we want it to be in. But all the same, if you run a given job on 4 cores, then it does it in substantially faster than it does if you run it on 1 core. So if you really need that result as fast as possible, and you've got 4 cores, then even core scalability can give you something better than you had before. Okay, so now the last part of the talk, I wanted to introduce a few concepts. If you're thinking of doing serious programming in concurrent programming, then you need to be aware of these concepts. So I'm not going to show you exactly how to use them, but I wanted to introduce them. So if you want to launch stuff in the background, then this concept of tasks and futures is really nice. So the idea is that instead of making a function call and then just waiting for the result to come back, you make a function call and you get a thing called a future, which tells you that at some point in the future you'll get the result from that function. And the function itself gets a thing called a promise, which it has to fulfill, and then once it's ready, the result just pops back into this future. It's a placeholder for a result that you get in the future, and you can do things like you can check if the result is ready, you can wait until the result is ready. When you get to the point in your code where you really need that result, you can just wait. So I've got a few little examples of what it looks like to use this system. The first is in C++, and you might think, well, why are we going to C++ if that's a hard language? Well, this actually looks easier in C++ than it does in Python, believe it or not. So here's my toy function. It's a big calculation. It's going to take a long time. It takes a single argument, and it returns a single argument, which just happens to be a double. If you want to run that asynchronously in the background and get a future, then this is the code that you need to write instead. It's not much more complicated. You have this keyword async. You put your function name, you put your arguments following it, and you get a future to a double instead of the double. You have to include file. And then at some point in the future, you call get on that future, and it gives you the value. And of course, you can do other things concurrently while that's going on. You can do this in Python as well. Slightly surprisingly, the code to do it in Python is a bit more complicated. You need to use this library, concurrent futures, to do it. And you need to start up a thing called an executor, which sets up a thread pool or process pool. In Python, it's best not to try and use threads to do this, because Python has a thing called the global interpreter lock, which makes multi-threaded programming a bit of a pain. But the process pool will actually start up a completely new Unix process to run the background task, which runs in a completely new Python interpreter, and then will feed the result back to the future. So it's actually very easy to write code to do this sort of thing. So that's one of the models that works really nicely if you're writing concurrent programming. If you want to, we need to think in a different way to write programs concurrently. So this is my schematic of what sequential programming looks like. We need to blow that out of the water, and our programs need to look much more like this. We need to have little modules of code which are sequential, and they need to be quite small, quite fine-grained, and they need to communicate with one another in ways that don't crash the system and don't cause contention and lots of waiting. Scratch is great for this because kids are now seeing Scratch, and in Scratch you do exactly this. You write little bits of sequential code and you attach them to sprites and parts of the system, and then the system pulls them together in ways that you don't really understand. But it's actually, I think this is great because it's teaching children how to write code the way that we now need to write code, not big monolithic sequential programs, but small sequential segments that are joined together intelligently. The last thing I'm going to mention is this idea of asynchronous queues, and they're a bit complicated, but they're kind of essential if you want to be able to run things in the background. The way that it works is that you have some client code, which is your main bit of code, and you've got a server that you might just have created that's its aim is to do something. And the way that you get it to do things is to feed things to it in the queue. So you have a message, M1, and you get a future back, F1. We have a message, M2, and we get a future back, F2. And then at some point, we can do it 3 times. And then at some point, our server will process the first message, it'll work on its stuff. It'll fulfill that first future, so we get a tick by our first future. And then at some stage, it fulfills the second message, and it ticks the second future. So that's a way of having something that sits in the background. It's not just a single task. It's a thing with state, an active thing with state that's doing work. And we can feed it instructions asynchronously, so we don't have to wait. And then we get back futures, which at some point in the future will get fulfilled. And we can test them, or we can wait for them as we see fit. And it allows you to do prioritization. If suddenly something really important comes along, it can jump the queue and get in there early. You can also do this with two-way queues, which is the traditional Unix way, without using futures. But I think futures are a really simple, powerful concept that actually makes this kind of coding much easier. Okay, so I have a kind of a demo which you can look at the end of this talk if you like, and it's called Sirius, the robot dog, and he uses these concepts to work. So we have a main thread which sets up this thing called a video controller, which is given a heartbeat every now and then, asynchronously. And it has a little image capture process, which again is separate from the other processes. It has a thing called Face Finder, and it will capture images, it will look for faces and it'll actually look you in the eye. It's a dog that will look at you, even though it's a robot. And underneath, it's also using OpenCV with OpenMP, so it's using all of the concepts I've just discussed here. And I can show that to anyone who's interested in this, and you can see the different processes lighting up as it works. So if you want to do this stuff successfully, then you need to make use of what Unix gives us. Thankfully, we've got all the stuff in Unix for concurrent programming. It's great. We should use it. There are also ways around. If you want to do message queuing, then there are ways that there are systems that will help you with that. Doing it yourself using TCP sockets and things is a real pain. You have to write a lot of code. But there are packages like ZeroMQ, which is a really good one, which will give you all of the infrastructure to be able to set up message queues, send messages back and forth in just a few lines of code. And if you're serious about building big complicated systems, then you should try and pull in some big infrastructure, such as the robot operating system if you're designing a robot. And also you can use built-in concurrency, so there are a lot of packages that you can recompile with OpenMP, and then when you fire up a job, it'll run on all 4 cores using OpenMP. And I thought I'd leave you with a few top tips. When you start writing something, think about concurrency. Don't write a big sequential application and then have to rewrite it to make it concurrent. Do use modularity, so make things small, independent, and then build your programs from lots of small components. That's composition and separation. And do use techniques like these futures and message queues. Don't play with raw threads. They're a nightmare. They're the reason why whenever you start applications like Outlook, it just crashes on you and it sits there doing nothing. And don't try and share memory and use mutexes to access shared memory. That's the way that people have been writing applications that have failed for the last 20 years, and it's not a good road to go along. And most importantly, if you want to know how much time you're gaining, just keep measuring those graphs that I put in earlier. They tell you whether or not your concurrency is actually giving you anything. That's all I was going to say. I'll leave you with a slide of links. If you want to photograph it, then these are good places to go if you want to do any of the stuff that I've been talking about. And if anyone's interested, then I can show you Sirius and how he uses his 4 cores. Thank you.
Do you have any questions?
I've had a problem with concurrent programming. Well, I think it is. I've read a keyboard scanner, keypad scanner, and if I try and use interrupts, they don't seem to keep up. But if I use polling, it works fine. Is that a feature of Unix in that interrupts don't work properly, or what? Maybe ideas?
I don't think I've got it. I mean, interrupt should work on Unix. I don't know what's wrong, I'm afraid. Okay. I mean, polling is fine, but it's active. It's much nicer to get a signal back when something happens. I don't know, I'm afraid that's too specific for me.
That's fine.
I've got a load of individual PDF files which I want to squeeze together into one program. One book, if you like. Now, I have found a way to do that, and funnily enough, you mentioned it was called the Convert program. So you can do Convert 1 PDF, 2 PDF, 3 PDF, 2.
That's ImageMagick Convert.
Yeah. Now, my question is there a way that I can do that in parallel, on multiple processes rather than sequentially the way that I'm doing it at the moment?
So the convert is taking, you're standing 1 on each time?
Yes. And then giving it to a file name on the end. But it doesn't exist.
Yeah, I mean, you could try and, so you could do a kind of so you've got a very large number of PDFs,
yes,
and you want to run them all together. So once you've got that list, then you can split it binary-wise, and so that you define a function that takes your whole list, and if it has more than a certain number in it, it will then split the list into half and then fire off 2 processes, and you can do that asynchronously, which would then
so that would mean running 2 jobs effectively, wouldn't it?
No, but this can be done recursively. So if you have a function that takes a long list and splits it in half, and only actually processes it itself once it gets down to a certain size, you can give it thousands of PDFs.
Yeah.
It'll split it into two jobs of, say you give it 1024, it'll split it into two jobs of 512. It'll re-enter the function, which would then split it into each of those two jobs into two jobs of 256. So you get a kind of a tree of recursion going on. And then once it gets to something that's small enough, then it'll say, well, I'll just do the work and do it as a sequential program. So that way, that's a good model to use for a lot of problems that can be split up in that way. And you could do that with tasks and features, so and it wouldn't take much code at all.
We're doing a robotics thing at Socialite and Pi Wars. So we were thinking of using Arduino as a separate cores to do parallel programs, like you said. But would it be possible to do that on a Raspberry Pi just using the different cores? So have one driving sensors, one with motors.
So what is it you're trying to do in those? What are the parallel jobs that you're talking about?
It's got a distance sensor and motor drivers. So the issue I've seen with some robots people have made is when the distance sensor reads, it stops the motors going.
So that's probably because the whole thing's been written sequentially. So you need to do something a bit like this, where you have a controller for each part of your system. So you have a controller that's doing the distance sensor stuff, and it receives requests. So you have a message queue, and you send the request into that controller. Say, give me give me the proximity number, whatever it is, and then it'll come back with its answer in the future, and give you the answer when it's ready. And so you need to build a system that looks something like this.
So the answer is the way the program was originally written, rather than...
Yeah, it's not a fundamental limitation of the Raspberry Pi. The Raspberry Pi has 4 cores, and actually these things won't need a whole core each. You know, typically you'll have maybe a dozen of these different parts of the system all doing something different. And they'll only need a fraction of the CPU power available for one core. But as long as they're all running as separate processes or separate threads within a process, and communicating back to the your main controller, your brain that's making the decisions. And the question is how to do that. It's hard. It's very hard to program from scratch. That's why you need these sorts of components to help you. So you exactly. Now I don't know enough about your system to give specific advice, but the way to do it on the Raspberry Pi 2 or even a Raspberry Pi with one core would be to set up something like this, where each of these is operating as a separate process, and they just pop up and do what they need to do, and then they send the results back through the queues.
Do you think it would just be easier to write several individual codes and have more than one Raspberry Pi or Arduino feeding back to a single main controller, so more of a delegating?
It probably isn't easier to do that because you still have all the communication. So then, even if you've got multiple Raspberry Pis, then you've still got to do this. You've got to do the sending the requests, receiving the results stuff. So it's actually easier.
Probably
within
worse by having multiple Pis because of the issues with communication between them. Having more than a single Pi, it's all within that Pi that's communicating. So it's all within the same OS. So you haven't got the delays that you would have with the other communication.
I mean, the bad news is that none of this stuff is really easy. But the good news is that there are a few tools coming along that make it moderately easy. And this is an example of it. In C++, that async command is just a piece of magic, which means that you can write almost the same thing as you did in your sequential program, but it will execute asynchronously. And there are a few other pieces of magic around that help you with that. But and I don't, what are you programming? Are you programming Python?
Python for the Pi, yes.
So it will look something like this. If you use this model, then you can have your background jobs which check the sensor, which do whatever the task is, and you can fire them off, and then your main program will remain responsive, and it will be able to, because it's the lack of responsiveness that you're talking about. That's the problem, isn't it?
This would be a good way of doing it. Yeah.
With Python, can you easily create a crystal set?
So can you easily create
A critical section of code, i.e. a section that cannot be interrupted. Because some
I'm not
sort
sure.
of obscure sensors that are very time critical.
Yeah.
And that's why people use Arduinos, because there's only one thread on Arduino, so it never gets interrupted anyway.
I don't know about that. Sorry, I've never tried it.
I think
that
probably in
sounds-
that case is you would run your Arduino for those time critical bits.
Sure, but you ought to be able to do it with a Pi as well, if you had an interruptible section of code.
Yeah. But with Linux, it's
It's fundamental. It's a preemptive multitasking operating system. So all forms of Unix use preemptive multitasking. So there isn't really such a thing as an uninterruptible process.
Exactly.
It's not a real. It's not something that you can use to build real-time systems, for example. Not absolute guaranteed real-time systems.
Hence why we use Arduinos for some bits. But then you could cut down the number of Arduinos you have by those bits that aren't time critical. Use the Pi, do this parallel processing, or concurrent processing, I mean, and then use the Arduinos for those bits, the sensors that are time critical. Pass them in with concurrent programming. You have those concurrent programs then talking to the Arduino and passing into the core program.
I mean,
Yeah.
I mean that's probably the easiest. If you've got the potential to have both systems there, that'd be the easiest way to do it. I mean, there are ways of using the Raspberry Pi without using it under Unix. You could use RISC-OS, which has a cooperative multitasking, and then you do have the potential to have something that's uninterruptible. But well, you need to talk to someone who's done that to find out how difficult or easy it is.
The problem with the RISC-OS is getting the interfaces to the GPIO and stuff like that. I've never used it, but anybody here use RISC-OS?
A long time ago.
I ran away crying.
I think there's a RISC-OS users group in London.
But the limitation is the fact that it's Unix. It's running, and you know, pretty much everything you do on Raspberry Pi is using Raspbian, which is Unix, which is preemptive.
Even those things that XPMC, that's Unix under the back and undercovered anyway.
So you can get the appearance of real time. I mean, as long as the timings are generous enough, then you can stream fairly reliably. You'll never get 100% reliability. You might be able to say if you have 99% reliability, you'll be able to guarantee that you don't interrupt streams more than so often. But you can't make absolute guarantees about real time and non-interruptibility under Unix.
Any more?